Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, Jam, how you doing today?
I'm good. How about you?
I'm great. I've been having a more chill week because I finished all those 1 million assignments that I had.
Nice.
So that's exciting. And I still have work to do, obviously, and I'm likely going to be teaching assistant over the summer and all of that, but I'm kind of on a little bit of a summer break. It's just less stressful work, you know.
That's so nice. Yeah. That's very nice.
Such a great time.
Yeah.
Well, I'm very excited about our topic today.
What is it going to be?
The topic for this week is a question from your wife, Emily.
Uh-huh.
And we got a message from a high school chemistry teacher named Steve S. And they both asked the same question.
Nice.
Their question is, how do color changing mugs work?
Oh.
How do they change color?
Right. How do the color changing mugs change color?
Right.
Interesting.
So I'm pretty excited about this. I didn't know, but it is, of course, very chemistry related.
Yeah. It's got to be.
Gotta be.
Somebody, I know somebody who says that like chemistry, like everything's chemistry related. I can't remember who said that, but somebody was saying that.
Do you?
Yeah. I heard it somewhere. I think I read it online, maybe.
Probably.
Yeah.
Probably not anyone you know said that.
Right. Yeah. It sounds just too grand of a statement to really be somebody I know. It's got to be like maybe Da Vinci or something like that said that.
Well, the very basic answer, the basicest answer that I can give you is that some molecules change color in different conditions.
Okay.
So that's like a super, super, super very basic answer. And people already maybe knew that or sort of thought it was true.
Mm-hmm.
But when you think about it, it's pretty crazy. Because when I think of molecules or compounds, I think of their color being fixed, you know?
Yeah, so some of these other ones are just allowed to do that whenever they want to, or what?
They're just allowed to do that whenever they want. I mean, something specific conditions change them, and we'll talk more about that.
Okay.
And some, it's just with temperature.
Okay.
So that's the very basic answer.
Yeah.
So I found a great article on the use of thermochromism, which is the technical word for changing color with heat, thermochromism.
Okay.
Or thermochromic.
Mm-hmm.
So I found a great article using thermochromism in commercial products, and it sort of just explained the chemistry of different ways that they do that.
Mm-hmm.
So there are two main ways. One is something that I think some people have probably heard of before. At least someone I knew who wasn't a chemist knew about it. And I thought, okay, maybe some people have heard of this. I hadn't heard of it before.
Yeah.
And that is thermochromic liquid crystals. So basically they're crystalline, but still in the liquid form, and their structure can rearrange when the temperature rearranges.
Weird.
The way they interact with each other. Yeah. We're not going to get into that today because there are a lot of other applications. I think it would be worth it for us to do an episode on that all by itself.
Okay.
So that can be in commercial products. But another one that's used in commercial products is organic dyes. And as an organic chemist, I personally think that's more interesting and fun. So we're going to talk about how organic dyes work. So the reason this question came up is because, well, from Emily, I think Steve just was interested, is because Emily has a mug that has Mr. Rogers on it. We love Mr. Rogers in this house, in our houses.
Yep.
Me, Jam, and Emily.
Absolutely.
If you haven't seen the documentary or the Tom Hanks Mr. Rogers movie, go see it right now.
Yeah, stop listening to our podcast right now. You can pick it up later and go watch those movies.
I agree. But come back and listen later so you find out how the mug works.
And it's a lot to ask of you to watch 2 movies in a row in the middle of your day when you thought you were just going to listen to a podcast. So maybe we'll be a little lenient. Just please do it.
Or just add it to your watch list, maybe. Anyway, so after we saw these movies, I got Emily this color-changing mug as a gift. And it's Mr. Rogers, and he's got his suit jacket on. And then it changes into his cardigan, just like he does.
Right.
And it's the nice yellow cardigan.
Mm-hmm.
So we're going to talk about how these mugs work.
Yeah.
And then I'm going to tell you specifically how that applies to that color changing mug.
Awesome. Yeah. I've seen this mug change its colors many times because I'll make coffee for M in it, or I'll sometimes make coffee and then just pour it into it or whatever. And it's kind of fun to watch it change. Sometimes it starts from the middle and then goes out depending on how hot the coffee is, or how much you pour in at once or whatever. Or if you put if you put creamer first, then the bottom's cold, and then it's kind of interesting.
We can post a video of it changing colors. I think that'd be fun.
Let's do it.
So thermochromic mugs, my understanding is they don't use the liquid crystals as much, and that there's more of the use of these organic dyes in those, but I'm not positive. But based on how I know Emily's mug works from observing it and the information I read, my assumption is that mug in particular is an organic dye. So honorable mention to the liquid crystals, and switching gears to focus on the organic dyes.
Okay.
And these are interesting, and part of why I really wanted to talk about them is because actually organic dyes don't change color because the temperature changes.
Oh, weird.
I know. So they actually change color based on the acidity.
Oh.
So more acidic or less acidic will change the color of the dye.
Huh.
And usually the dyes that they use in these organic dye thermochromic mugs are what's called Leuco dyes. I think that's how you pronounce it. It's Leuco, Leuco dyes. And what that means is, at least under some conditions, they are colorless. And other conditions, they're brightly colored.
Okay.
Now, I want you to think all the way back to when we talked about color and bleach and antioxidants. Those are 2 episodes. We talked about the same things.
Mm-hmm.
And remember, color was due to those alternating double bonds.
Right.
That allowed it to absorb light in the visible region and reflect back light in the visible region.
Right.
The name for those alternating double bonds was... Can you remember?
Oh, man. Let me think for a second. The name for the alternating double bonds. Can you give me like a small hint? Is it possible even to do that?
Starts with con.
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 Man, I gotta get this. Is it conjugation?
Yes.
Oh, weird.
So those conjugated double bonds is alternating double bonds. And when there's enough of them, the electrons move around on this electron highway almost. Mm-hmm. They have freedom to move around, and they absorb, because of that electron movement, they're able to absorb in the visible region. Okay. So these dyes, these Leuco dyes that are sometimes colorless and sometimes very colored, highly colored, the way that the acidity changes those color conditions is basically it interrupts the conjugation or lets the conjugation happen. So I thought of it almost as a floodgate.
Oh, wow.
So under the right conditions, they put up a blocker, like a dam, so that water can't flow, the electrons can't flow.
Yeah.
And then under other conditions, that's open and the electrons can flow.
Oh, wow. Okay, got it.
So when it's blocked and the electrons can't flow, the conjugation is cut short and those compounds don't have the color and they become colorless.
Wow, weird.
But when you open the gate, the electrons can move freely and then their high color is back.
That's crazy. So wait, what is it that's actually like blocking, doing the blocking?
So that might be a little complicated and a little beyond the scope, but I try to think of it as almost like what we saw in bleach when the electrons were following this highway of the alternating double bonds and then we'd break a double bond to make it a single bond.
Mm-hmm.
And then the electrons could not flow anymore.
Right.
So it's basically that same thing, only it's a reversible reaction.
Okay.
So you can break it or unbreak it. You can stop the flow or open the flow back up. And based on the organic structure, there's a lot of different ways you could possibly accomplish this goal of making the electrons flow or not.
Yeah.
Does that make sense?
Yeah, it does. And it's interesting to think about it kind of at first, it's already blocked. And so really, it's like almost like the flow gate's already down. You're trying to find a way to raise it. Rather than it being like, there's this color happening, we have to stop it. It's more like, if we can remove this thing, we can allow the color to happen. That's like so weird.
I know, it is so weird. I don't know why. I've thought a lot about how some things work and wondered at length. But until we got this question, I had never wondered.
Yeah.
Now I'm thinking that is insane, actually.
Yeah.
That these molecules would just change color.
Well, especially,
so
I love to think about how like this is so fascinating. And in this specific application, it's just for fun.
I know.
It's just fun to have a mug of Mr. Rogers that does this. And it's like, surely, obviously, this was discovered in some other cooler way, in a way that was like, maybe there's a different application for it, or, who knows? And I bet the intent was not. Now, wouldn't it be nice if we could have some mugs that could just change some color for once? Like, geez, look at all these mugs. So boring. Come on.
Well, I will say there was mention of them using the other dyes in medical applications, but also they talked about how they've made a thermochromic thread now that can be knitted with, that just changes color based on the temperature.
What?
I know. And they talked about how a lot of these things were developed by manufacturers and used before they understood them. Like even now, there's a lot of unknowns in some of the more complex versions of the organic dyes.
That's crazy, man.
I know. Just the way the paper said it was kind of like, so you guys are just throwing stuff on and you have no idea how this works. That's crazy. But I mean, there is enough understanding to know how some of it works,
Right.
And to have the basic idea. But I just thought that was funny.
That is funny.
So circling back around, we've talked about the fact that there are color changing mugs. Some commercial products use these liquid crystals whose structure rearranges, the way the crystals are formed rearranges to change color. Honorable mention, not going to go into that today.
Okay. Yeah.
And another one is these organic dyes. And these organic dyes have either multiple or one dye that's colorless at different conditions of acidity, or highly colored at different conditions of acidity. And the way that it goes back and forth is depending on if it's acidic conditions or not acidic conditions. The electron highway is open to have all kinds of movement and good light absorption in the visible region, or the electron highway is closed off, floodgates closed, the electrons can't get through, and then it's going to be colorless. It's not going to absorb in the visible region.
Right.
So that's where we're at to this point. But we have to answer the question. How does the acidity change with heat?
Yeah. How does it?
Jam's squinting his eyes like, wait a minute.
It's like, yeah, wait a second. You haven't explained the most important part yet. You can't pull one over on me.
I can pull one over on you. You were going to let me off scotch-free without explaining that.
Well, if you hadn't said something about the acidity having to change and it not being heat, then I might have not thought to ask about it. But
that's true.
That plays totally against my expectations about how these things work in the first place. Like, the most fundamental part of it that any of us lay people would say, like, oh yeah, it's because it's getting hot or whatever. Like, well, not exactly. That's already enough to be like, okay, interesting. I'm already wrong.
Yeah, I know. Well, and I didn't even really think about it either, as I probably should have, but it didn't even occur to me that that's likely what it would have done. So there's a concept in chemistry called equilibrium. Do you remember that from taking from taking general chemistry?
I don't. That's not really coming to mind. I feel like I've just heard that word a lot, but like describing back to you what it meant and when what I was taught about it, I can't. Nothing's coming to mind.
Well, this is an idea that is based sort of in the fact that chemistry is atoms and electrons, and things are constantly moving.
Mm-hmm.
We draw it on paper like A plus B equals C. And I think it can be easy to imagine, like, we take eggs and flour and all this stuff and mix it together, and then we get cookies, and that's it.
Right.
But really, in chemistry, things are moving around so much that A plus B equals C, but that C can break back up into A and B, and a lot is happening all at once. There's a lot more going on than just we mix these ingredients together and get cookies. It almost would be more like the ingredients are mixing and making cookies and then breaking back up and going back to the ingredients and then making cookies again. And it just goes back and forth, back and forth. But eventually it will balance out to reach an equilibrium. And that's different for each reaction. The best way I can kind of describe it is usually there'll be more of either the products or the reactant. So there'll be either more cookies or more ingredients depending on what the reaction is.
Got it. Is it a similar idea, or is it not even close to, like, in biology, anatomy, like homeostasis, where things are kind of ebbing and flowing a lot, but their balance is trying to be struck in some way?
Maybe. I don't know much about homeostasis, so that makes it harder to answer that question, but I think that's kind of a good idea of it.
Well, I'll tell you this. You should look into it. It's really cool, and everybody's doing it.
Everyone's doing it because your bodies are doing it because you have to be at homeostasis to survive.
It's very popular.
I just had to think through that joke real quick. So maybe homeostasis is close because in the end, when an equilibrium is reached, it's like there's not a lot of concentration change after that.
Okay.
But you can use certain things to sort of push an equilibrium to one side or the other. So, for example, if you're making carbon dioxide in your reaction and you keep it trapped in, that's carbon dioxide's a gas. If you keep it trapped in a bubble, carbon dioxide is made. Eventually, probably an equilibrium will be reached with the carbon dioxide and the reactants. But if you open up your bubble, the carbon dioxide is going to be flowing away and all the products are going to react until they're all gone because no equilibrium is going to be struck up.
Got it.
So that's sort of an example of controlling equilibrium. You learn equilibrium in general chemistry and you learn about Le Chatelier's principle, which is how you can kind of control it. But it's a pretty complex topic to focus on top of our thermochromic mug discussion.
Got it.
Because we're talking about electron highways, conjugation, we're talking about acid and base, and we're talking about equilibrium. So this is a little bit of a lot of concepts that we have touched on.
Right.
And then equilibrium is the new one.
Okay.
I would be surprised if that didn't come back up. But in this instance, they essentially use heat to push the equilibrium to one side or the other to make it more acidic or more basic, because the acid and base is going to be present in equilibrium and you can push it to one side or the other.
Got it.
Does that make sense?
Yeah, it does. So basically they've kind of been able to either arrange it to where, or they just found out this is the case, that, like you're talking about, sometimes they didn't really know how it worked, but where just the presence of heat is able to nudge that equilibrium more toward the acidic side, you said?
So I don't feel with confidence I can say, without knowing a little bit more, which side of the equilibrium the heat would shift it to more acidic or more basic, just that the heat will shift the equilibrium. Okay, so that's a lot.
Yeah.
But that's it. So most likely in your Mr. Rogers mug, you pour that coffee in. and the heat starts this chain reaction of changing one thing that changes another thing that makes a color change.
Man.
Do you want to explain it back to me?
I do. This is a tough one. It's more complicated than I expected. I'm not really sure what I expected from the beginning.
Well, I think it's a little bit complicated because you've got 3 big organic chemistry topics actually present.
Mm-hmm.
And so I'm trying to kind of rein it in to where we're not digging super deep in all 3 of them,
Mm-hmm.
which makes it a little bit harder because we're just skimming the surface of them and how they work together.
Yeah.
But you can go more in depth, like on the conjugation one back in our episodes on bleach and antioxidants.
Mm-hmm.
And you can go more in depth on acid base in our conversation on what makes baking soda and baking powder different.
Mm-hmm.
So you have other things that you can go back and learn more. And then you've got this new thing about equilibrium also mixed in.
Yeah.
So I'm doing a lot. I'm just throwing a bunch of stuff at you right now.
I think I can do it, but see what happens. So
I believe in you. I tell my students I believe in them before every exam. So this is your exam, and I believe in you.
Okay. Thanks, Mr. Rogers. So, okay. If you know what's good for you, you drink coffee. And when you drink coffee and you use your Mr. Rogers mug that we all have, you pour the coffee into it and the coffee's hot. And that's just part of it. It's not really the main reason, but it's just part of the beginning of this process where that, kind of going backwards here, but that messes with the equilibrium in this coating on the outside to where these highways can open up. I like the floodgate analogy. I was thinking we were like, traffic is a good one too, where there's like construction. And it's like, I live right off a road that was like under construction for like years. And
yeah,
it was just so rough. Now it's one of the fastest ways across town. Because like if you just remove all that stuff, it's in the way and you have a straight shot, then it's way faster. So then these electrons are able to move really fast or whatever, freely. And then they can absorb and reflect light, which is a callback to the main topic of another episode, which allows them to then, rather than being clear when we're looking at the mug, actually able to absorb and reflect the yellow. Oh, it's not absorbing yellow light. Oh, man. Isn't it like the
it's
opposite?
absorbing on the opposite and reflecting the yellow.
It's absorbing the opposite and reflecting the yellow. And that is it, I guess. I don't know. Man, dude, that's tough.
Yeah. You did great. I think that was a great explanation. The traffic analogy is a good one where it's just clogged up here and cars can't evenly flow through here, and that keeps it from functioning in the same way.
Mm-hmm.
So when you open this or close this construction site, your electrons can flow or they can't. The structure of the compound doesn't maybe matter as much.
Yeah.
And I can maybe put a picture of a dye and show you where the highway is blocked off and the highway has free flow.
Yeah.
That might be nice for you guys to see. It would maybe be confusing to see organic structures, but it might be fun.
Yeah, that'd be helpful, I think. But I did not
I think you did a great job.
I did not give a shout out to the other type of, what's the word? Don't say it. Thermochromatic?
Thermochromic.
Which is the crystals. In this case, this is the organic dye.
Right.
Sweet.
The crystals is our honorable mention. The organic dye is the one you described.
Shout out Thermochromic Crystals. Love you. Love your work. Don't have time to go into it, but just shout out. Keep doing your thing.
I will say my suspicion is that actually it was the opposite of what you said. I think the coating on Mr. Rogers is the part that is the dye. So it's the black suit, and I think that heats up and the color becomes clear.
Oh.
That's my suspicion, because when I looked really closely at it and sort of felt the texture, that's the part that seems different. And the way these dyes work is they have to be suspended in some kind of thing that can be put on and held as a solid state on your mug. So I think that is actually the colored part, but that's pure speculation.
Interesting. Dang, yeah. Weird.
Could be either way. I'm not 100% sure. That's just my instinct.
Dang, that's crazy. It's weird to think which one, like, obviously we know when we use it, it starts out one way and changes to another. And so we just think like, oh yeah, it's got to be it. It's like, that's the way it is. But if it's really the other way, because that's the easier way to make it happen with science, it's just like kind of, it's kind of weird. And
it could be either.
And we're already one step removed from what I expected about this kind of thing, which I thought just the heat's fine. That's enough. It's like, no, sorry, heat causes a thing that causes a thing that causes a thing. It changes
well,
the
and
color.
That's kind of why I wanted to do that, is because I think it would be easy for people to be like, yeah, heat changes things. And then it wouldn't feel as like a fun new thing.
Yeah.
But I was surprised when I found that they actually do basically a combination of the dye and then they call the acid changing conditions a dye developer. So I didn't know that they had those two things and they could, change the color that way. I learned too. And that's when I think it's exciting.
Dang, that's crazy.
So, yeah.
And it was right under our noses. This crazy scientific advancement was in our mugs, and I feel like I even had like a pen or pencil or something like that like when you're holding it and it changed colors from the heat of your fingers. Just stuff like that. That's like we've always had as kids growing up.
Those also could be using the crystals as well.
Oh, right.
I'm not sure how to look. I don't know enough to know how to look and know like these are the crystals and these are the, I don't know enough to know that, but that's it for the chemistry.
Man, kind of crazy. That was not a very straightforward thing. It had twists and turns and ups and downs and revenge and political unrest. All the makings of a good story.
There was some political unrest in some previous episodes, but thankfully none here.
Yeah.
Yeah, it was all the makings of a good story for sure. Well, is there anything from your week that you want to share? Anything happy happened to you this week?
It's been a lot of just being at home like everybody else, but my wife and I did get to celebrate our 5-year anniversary this past week. And so we probably didn't get to do the kind of stuff we'd normally want to do and like, go fancy dinner, that kind of stuff. But really cool to get to talk about that together and think about how fast these 5 years have flown by and just kind of talk about some fun memories and stuff like that. So always cool to get a chance to reminisce a little bit and kind of makes you thankful and reminds you of good memories you kind of don't think about every day or whatever. But yeah. So really glad we've made it to 5 years. It's awesome.
That's so sweet. Congratulations on 5 years. Happy anniversary.
Thank you. Yeah. Anyone could do it. You can do it.
Anyone could do it.
Yeah.
I don't know. Marriage seems hard. I think it really is a sacrifice and trying to care about the other person and find compromise, So
True.
That's impressive.
Yeah, I wasn't trying to say it's easy, but I do think anyone can do it.
Anyone probably could do it.
Yeah.
Well, I'm impressed. Congratulations.
Yeah, thank you. What about you? How's your week been?
Well, I too have been in a relationship for 5 years, a relationship with my education, graduate school education. For those of you who don't know everything, I was working on my PhD in organic chemistry, and then I decided I just really loved the science communication and education research side of things. So I switched over, which means that I kind of had to hit the reset button. And a big milestone is finishing your written qualifying exams and doing an oral exam where you present a big proposal of some research projects and you ask a lot of questions. And I finished up, I think, hopefully if I passed, my last few written qualifying exams, which I'd already taken for the first PhD I was working on and didn't get. And so it's been kind of a whole convoluted time, but it's really exciting to be done with those.
Yeah.
And then moving on to the next step. So that's a pretty exciting thing. And I've, finished up my semester and finished those up really close together and have had a little bit of a break. And then now I'm looking forward to the next thing that's coming. But it is all weird, kind of what you're saying for your anniversary. It's just weird to have that big, exciting thing in the middle of such a weird time, and kind of worried about what's happening as the state is opening back up and being concerned about people's safety. It's just like a new world with this going on. And so just, kind of a bittersweet time where normally I would be so elated about finishing up that portion of things. And instead I'm just I'm happy, but it's just a weird time.
Totally. Totally. Yeah, absolutely. Definitely a weird time.
But I always love doing the podcast. It always cheers me up. And I'm so glad that we've been able to keep pushing forward remotely.
Yeah, absolutely. Thanks, technology, for being here for us.
Thanks, technology, and thanks, Jam, for knowing how to use technology. And thanks to all of you guys for coming and listening to this week's episode and learning about how thermochromic mugs work. I really loved it.
Me too. It was very interesting. And Melissa and I have a lot of ideas for topics of chemistry in everyday life, but we do want to hear from you. Ideas just like color changing mugs. So if you have questions or ideas, you can reach out to us on Gmail, Twitter, Instagram, Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share thoughts and ideas. If you enjoy this podcast, you can subscribe in your favorite podcast app. And if you really like it, you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/chem4yourlife and donate the cost of a cup of coffee.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode can be found on our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to A. Hefner and A. Kiwasong, who reviewed this episode.